Hello. In this video, I'd like to present information about the performance assessment completed in Mitch Ehrman's Calculus 1 class in November of 2020. This performance assessment was completed as a component of the MSSE 504 assessments class through Montana State University. The performance assessment I asked students to complete was a physical measurement of the diameter of vessels in several positions using dial calipers and height gauges, as well as completing regression analysis to develop functions that can be used to measure the volumes of these vessels using the solids of revolution method using integral calculus. I chose this analysis because many of our students are already familiar with these tools, and the results segue nicely into our next unit in calculus. Students have studied antiderivatives and indefinite integrals and are learning to use definite integrals to compute the area between a curve and the x-axis, but they have not learned about the method, the solids of revolution, but they would benefit from seeing applications of the definite integrals in this context. Therefore, the students' performance assessment was based on their ability to measure dimensions of these 3D models of our vessels. They were also assessed on entering the data into a spreadsheet, whether that was a Microsoft Excel spreadsheet or a Texas Instruments graphing calculator, and then ultimately to perform a regression analysis in order to find an equation that fits the data. A rubric was used to score their performance in measuring data points in establishing the regression, and the activity concluded with an introduction to the solids of revolution using definite integrals. Here's a copy of the rubric. You can pause the video here and try to read each component individually if you'd like. Otherwise, I'll just provide a quick summary. Essentially, there were 4 objectives that I was assessing students on, and up to 7 points were earned within each of those objectives. Among the objectives, there were generally 3 items that I was looking for, and if a student completed all 3 of those items, then they earned maximum credit. And I just recognized that this was my old copy. Let me switch here. This is the current copy of the rubric. So again, if a student did meet all 3 of these components within the objective, then they earned 7 points. If they met 2 of the objectives, then they were likely going to score 4. If they, in this example, completed the height measurements but didn't meet any of the objectives, they may have been given 1 point. In each case, though, I did provide an opportunity to provide other comments if there was a reason why I felt a student fell into one of these columns other than what was described here. I provided a comment on those rubrics. Or if I felt that a student should have been awarded, say, 2 points instead of 1 for some additional work, then I could have noted that here as well. Students in my building only attend class once per week for 70 minutes, so it was pretty busy the day of this activity, and I didn't take any pictures while we were working. But these 2 images represent the tools that were used in class. This item on the left here is a height gauge, and this heavily weighted base sits on a flat surface, and when zeroed properly and calibrated, this point will accurately measure the height of a position or an object above the surface of the table. And on our examples in class, we did have dial gauges that were reading in centimeters, and they were accurate to the thousandths place. They were very, very precise. Similarly, we used dial calipers to measure the diameter of the vessels. They were very similar to these as well. Again, they measured in centimeters and were accurate to the thousandths place. These jaws can be slid open or reduced in width, and essentially the distance between these 2 points is related on the scale and dial. Instructions were given to students the week prior to this activity, and they were told that they would use the height gauge to measure vertical stations at regular intervals. The station just establishes regular height intervals so that we can measure the diameter at those specific locations using the dial calipers. The data points collected by the height and diameter would have been were transposed and recorded into a spreadsheet so that the data points would reflect or illustrate the vessels laying on their side, and the profile would be presented in that way. So here are some examples from the class. I had 2 vessels and 2 teams per class. The students meet, some students meet in the morning and some students meet in the afternoon. So in both morning groups, the teams decided to measure their station heights at 1/2 centimeter. So they actually measured the diameter of these vessels up to 30 times, almost 30 times, because the height of the vessel in both cases was 14 centimeters, and the diameter data points were plotted here. These came from Microsoft Excel. And here are the data points that the teams recorded on the computer in the classroom that's attached to my smartboard. So one team created the data points for essentially a linear equation, and they used Excel to create that regression. Another team reported the data points of this curve. Now, if I recall, this vessel was actually established by using a sine curve, but the students opted to find a 5th degree polynomial to fit this data. I think they felt that that would have been easier to apply integral calculus to. Now, here are images of the vessels as they were being prepared to be printed on the 3D printer. This particular image here, you can see that there was a wall thickness to the object, and so rather than printing it with wall thickness, there's an option in our slicer program to just print the outside contours, and so that's essentially what the 3D printer did, and was able to print these objects pretty quickly and easily. So here's the straight-edged vessel, or at least a preview of it, and then the smooth curved vessel. So you could probably imagine that implementing this performance assessment was very difficult in the time frame that I had, and I don't really feel that a truly authentic performance assessment was achieved with this activity. It really wouldn't be appropriate for me to spend a significant amount of time on an activity like this, considering the limited amount of time that I see my students face to face, and we generally use that time for question and answer based on their other assignments and lessons that are completed outside of the classroom. So while I think as a performance assessment this activity fell a little flat, I do think that the performance component of accurate measurement was at least well recognized, and the students as a team were able to perform these tasks, but not individually. And then as a team, again, they were able to perform the regression analysis, and I think they did a pretty good job with that too. We were not able to complete the solids of revolution component in class, but I do have a group of students that are in our robotics lab. We call that mechatronics. And I did go down to their lab after this course was finished, or this class was finished, and we actually talked about the analysis. And with permission from their lab teacher, we were able to talk about this method. Now, again, the students are pretty familiar with computing the area underneath a curve. So this straight line we would still call a curve. We can find the area there, but this notion of these cross sections, these circular cross sections or disks stacked an infinite amount of times within this space, that's accomplished by what we call the disk method for solids of revolution. And so the equation, while it looks a bit intimidating, wasn't all that different from what they are starting to learn right now. And so with a little bit of trust, they kind of followed along with the 4 or 5 steps here. We were able to establish the suspected volume based on the morning team's regression analysis for the linear equation. We then spent a little bit of time talking about how we could do this using geometry. And while this component here was the vessel, we actually had to imagine the sides extended to complete the cone. And in order to find the volume of this, essentially a truncated cone, we took the volume of the full cone and subtracted this upper or lower cone in this case. And that left us with the volume for the vessel. And using that method, we ended up with a result that was remarkably close. So 604 cubic centimeters in each case. And so again, the students themselves weren't doing this work, but they were at least making the connections and seeing where the process was going to go. And then finally, I showed them one more time that the use of calculators and computers is greatly beneficial. While we as students and mathematicians may understand the process, we can rely on calculators to perform the work for us. And that's essentially what was done here for our curved vase, or our curved vessel. So we programmed the calculator to compute the same integral between 0 and 14 centimeters in height along this particular curve, and the volume for the curved vessel was established as well. Oh, and one last thing to note, we caught this after the fact, but all of our data points actually measured diameters, not radius. So in order to use the process correctly, the regression analysis that was completed ended up having to be divided by 2 in every case, because this formula represents the diameter of the vessel, not the radius. So that was a simple fix, but something that we were able to correct. So hopefully this alternative to the narrative paper worked well for you. I feel like I was a bit more comfortable in explaining this situation rather than writing it up in a paper. If you've got further questions, by all means, please let me know. Otherwise, thanks for watching.